So the first part of this lecture series is going to be going over some of the mathematical prerequisites. The first stop in that is some basic trig. So you would have seen this in Leaving Cert and maybe even Junior Cert. So it's nothing you haven't seen before. But it's a good idea to just make sure it's in your head and everything is very solid in that. So to start off, we're going to define our three main trig functions and see what we can do with that. There are more, but they're really just combinations of different trig functions and inverses and that type of thing. So if we start off with a right angle triangle here, we denote this angle being 90 degrees by the box with some angle theta between these two. And we can draw up, let's call this side A, this side B, and this final side C. So we can define different trigonometric functions, they're called, by different ratios of the different sides. So we can call sine theta is the side opposite to the angle over the hypotenuse, so this long side here. The cosine of theta as this bottom adjacent side to the angle over the hypotenuse, and the final of the main three trig functions, tan theta as sine theta over cos theta, which, when done out, will simplify to A over B. Right, so now that we have our trigonometric ratios defined, or trig functions defined, we're going to see how we can really use them. So we had this side being A, the bottom side, the adjacent side being C, and this hypotenuse, the long side being or being C. But we can instead imagine we have this right angle triangle on an xy plane, where this is the x-axis, this is the y-axis. So now this, right, great, a triangle on a plane, not really too important. But if we define, or if we say, imagine a circle here, not the best circle, but anyway, and this point being called P, which has some x and y coordinate, we can really see that this x coordinate, this how far along the x direction we need to go to get to P, is really the same as this adjacent side of the triangle that we've built. So we can, instead of calling it B, though, we'll call it x. And the same can be said for the opposite side in our sine function. It's really the same distance as the y coordinate. So if we want to go up a certain amount to get to P, that's really the same as this opposite side of the triangle. So we'll call that y. And if we have a circle of any radius, really, the distance between the origins, so 0, 0 here, and our point P will be the radius of the circle. P is on the circle, or is on the actual circle itself. So we can define, or we can call this or for the radius. And now we can use this information and our trig functions that we've just gone through to find out more properties of the point or the circle. So if we knew, for instance, the angle theta and the radius, we could find x or y. The way that we do that is, say if we want to find the x coordinate, we have cosine theta is equal to x over or. And we can just multiply both sides by or and we get or cos theta is equal to x. And we can do that the same for the y coordinate, the y component, and we'll end up getting y sine theta, or sine theta is equal to y. So this will come up quite a bit whenever you're studying like circular motion or really anything that you can shoehorn in sine thetas or cosine thetas or circles or anything like that. So yeah, is equal to y. That's really the concepts behind trig. Most of this is done long before college, so that should be pretty good in your head. There are different identities you can use with these. So like sine theta plus cosine theta, sine squared theta plus cosine squared theta is equal to 1. Those can be found in your tables books, or online or anywhere else. I don't really think that you need to go through them. But yeah, that's really all the kind of trig that's important. So once you know where these all come from, you're pretty good to go. And then, as I said, anything using it like that, or any identities where you need to either add or multiply different angles together or anything like that, there are online or identities you can find online to mess around with that. The kind of next thing that we need to go over, though, is the idea of coordinate spaces. Or, yeah. Right, so the idea of a coordinate space is just something that we can use in physics or in maths to kind of quantify the amount that something is changing. In that we want, say, the position space, right? With the think of it as like the physical real world. This is x, y, and z coordinates, something that you might have come across before, but we use that even in the real world to tell the difference between something in one location and another location, right? So if we want to physically represent a physical difference in location in a mathematical way, we just need to define some way of giving these locations kind of information, some way of defining like this place as location A and this place as location B. And the way that we do that normally is through the 3D Cartesian coordinates, but we don't necessarily have to. So the Cartesian coordinates are the kind of x, y, and z component, or x, y, and z axes. So we have x, y, and z. This is what's known as an orthonormal basis. So the word orthonormal will come up again and again, especially when you do like linear algebra in first year. The word, or the ortho part of it, just comes from the fact that they're perpendicular or orthogonal. So the angle between the x and y axis is 90 degrees, the angle between the x and z axis is 90 degrees, and the angle between the z and the y axis is 90 degrees. So by ortho, we just mean everything is perpendicular or orthogonal. The normal part of it is a tad bit more difficult to explain without the idea of vectors. So we'll come back to that for the most part. But really, all you have to understand is that the x, y, and z has unit length. So each piece is 1 unit. So instead of if I move 1 block on the x-axis, that just means my x value is equal to 1. Whereas if we renamed the x-axis as the a-axis, where a was worth 2 of x. If I moved 1 step along the a-axis, I would have moved 2 steps along the x-axis. But that's not really important to go through now. That's really all we need to know about coordinate spaces in general. So remember that normal just means unit length. Instead of using x, y, and z, sometimes we'll use x1, x2, x3, but usually we'll stick with x, y, and z for like writing things out at least. The last thing in this first half of the mathematical prerequisites is the idea of vectors. Now, vectors are or can be a tricky enough thing to like grasp your head, get your head around, like the first time you see it. And if you ask somebody what they are, depending on what discipline they come back from or they come from, they'll give you a different answer. Like a physicist will tell you that a vector is any quantity with magnitude and direction. A computer scientist might tell you that a vector is just an object that stores information. A mathematician might tell you that a vector is just something that, or an element of a vector space. Now we'll really be dealing with the first one, and a quantity that has magnitude and direction. That's really all we need to know, but you'll come across the idea of a vector space and how that defines a vector in first year. So it's not too out there, but it's not really what's useful for us right now. So yeah, we can use different notation for a vector. So a lot of the times what you'll first come across as vector notation is just an arrow on top. So this means that the quantity v here is a vector. So it has some degree of direction involved, as well as like how big it is. Another notation is this one line underneath. This is usually the notation I write in, but it's not the notation that the notes are written in. Another type of notation you can see a vector being kind of written as is kind of like a bold. Not very good there, but some people will write vectors as a bold letter, especially when it's typed. It makes life easier. But those are really the three things that you'll find. But this first one here is usually the most common. So yeah, this is our different notations, but we'll really be using this first one for the most, or these first two for the most part. Okay, so if we think of a vector in a graphical sense, right? So let's say we have, let's only deal with two dimensions for now. So if we had the xy plane here, right? We imagine something, let's think about how we would represent an object that has magnitude and direction. So we need something that like shows, we need a way of showing if something has, is bigger than something else or smaller than something else, but also in what direction it's pointing and what direction it's going. So the way that we do that is with an arrow, right? We use a pointed arrow, usually coming from the origin, but it really doesn't matter where, to define, say, let's call this a vector v. Right, so this vector, now we have it coming from the origin because that usually makes things tidier, but when you think about it, we don't really have to, right? If this means that if this vector means that an object, let's say it's a velocity, right? Let's say an object is moving in, velocity is pointing in this direction, right? It's moving, let's say 5 meters per second in, what's that, northeast or whatever it is, it doesn't really matter. If we took this and we moved it along a bit, this is really the same vector, right? There's no difference in it's still moving in the same direction. It still has the same angle here. These are the same angles. And if we were to talk about from the y-axis, these are the same angles here. So there's no difference in direction. And they're pretty much the same length as well. So these are identical vectors in everything but where they are. And so there's really no difference between them. It's just how we usually notate them. So to keep things straight and to compare different vectors, we usually do keep them coming from the origin, at least if we can, just to make our lives easier. But if we had, so this vector v here, right? So we have a vector v. Now, what can we do with it? Can we add it, subtract it? Like, what can we play around with? So the first thing we'll look at is if you can multiply some vector by some random number. Numbers by themselves we call scalars as opposed to vectors in this case. So if we had, say, let's say some scalar a, can we multiply it with some vector v, right? Well, we can. This is pretty simple. One of the kind of first things you'll learn how to do. Now, if a is greater than 1, what will happen? What will happen here, right? If we think about this new vector as a vector w, how will the vector w compare to the vector v? Well, if we're multiplying v by something greater than 1, w will be greater than v, right? So the magnitude of this new w will be greater than v because we have to multiply it by a number greater than 1. But multiplying it by 1 or by some random number bigger than 1, that shouldn't really interact with the direction at all. Like, there's no reason that, doubling a vector should change its direction. If I'm going 5 meters per second in this direction, if I double that vector, why would I move in any direction but the same way? So that's why we can write this new w as this vector, but stretched along the same direction, but with twice the length, or with some a times the length. And if we have instead, let's say if a is, so we have that there, if a is greater than 1, and then if we are saying some b times a vector, where b is less than 1, what will happen then? So if you have any number and you multiply it by something less than 1, it'll shrink, right? If you have 5 multiplied by 0.1, it'll shrink. So if we have a new vector, let's call it u, and we're multiplying our original vector v over there by something smaller than 1. So it could be a half, it could be a third, it could be 0.9, anything like that. What will happen graphically? So how are we picturing this transformation? So if anything greater than 1 stretches the vector along its original direction, we can say that anything less than 1 will shrink it. So we have some vector u that is instead shrunk. So let's say to like about a half of what v was. That's pretty small, right? So if it's being halved or being third or whatever, some multiple of some scalar less than 1, we can say that this is now shrunk it. It's still going in the same direction, just like w was, but u is now smaller, or is a lower magnitude than v does. Right. So we now know that you can take a vector and you can multiply it by a scalar. Right. We've shown that this can be done. Okay. Now, what's the next step that we can try and have a look over? So what can we do with, say, just normal arithmetic normal arithmetic operations? So if we can multiply it by a scalar, right, we've checked that off. Let's see if we can add them. Add 2 vectors. Right, so let's say we have some vector u, say going in this direction, and some vector v going in this direction. So graphically, how are we going to try and add these together? Can we do it? Well, yeah. So the way that we can think about vectors is by movement, right? We like to think about it by movement because it's by our human way of thinking, our human intuition, it's very easy to. So if we say we move, let's say u, we move along u, right? So we move up this vector a certain amount, and then we want to move along v. We can move down along v, pretending that instead of this is at the origin, we can pretend that v is down here. Because remember, we decide where vectors can live in this way by any scalar, or by any scale. We don't need to put it at the origin, we don't need to put them anywhere. We can decide how that goes. So we now move up along u, and then down along v, and we're at a new point here. Let's call that P. So we've now combined u and v in a sort of way, right? Now instead of we can say that this is just u plus v, right? But that can get a little bit heavy, especially if you're going and combining loads of vectors together. So instead of talking about this as combinations of u and v, let's just call its own vector by itself, right? Let's just say this is the vector p. So instead of saying every time that we have to move along u this amount and then along v, we can just say we're moving along the p vector instead. So this is the way that we add two vectors. We can add any amount of vectors as we want, but we'll just stick with two because it's the simplest. The idea then is, can we subtract two vectors? So can we have a vector u and then subtract a vector v from it? Well, we can. And the way that we do that is by kind of combining the two that we've already done. So instead of saying, let's say we want to take u and subtract v, right? And we want to make this new vector, we'll call it q. Let's call it q. So instead of thinking of it as subtraction, we can think of it as adding a minus. So we write this as u plus minus v. And that's really the same thing, right? Because when you take this minus out of the bracket, it's the same thing. So instead of thinking of it as minusing, we're now adding two vectors together in the way that we just did. Now, what we have to think of is, how are we getting this minus v? And that's how we use our first one. We're multiplying it by, instead of a scalar 2 or a scalar 0.5, we're just multiplying it by a scalar called minus 1, right? So we can say that minus v is the same thing as minus 1 times v, right? And now graphically you might ask, how does this work? How do we, instead of scaling it by a certain amount, so we stretch it or compress it, how are we using a minus 1? Well, the way that that will work is by flipping it, right? So if this is how we can change the direction of a vector, but by multiplying it by a scalar. So we take a v, and then if we want minus v, we just flip it along the same line and completely parallel. So we can call this minus v. And you can think about this in the same way that if I'm moving 5 meters per second in this direction, and then I want to multiply that by minus 1, it's like moving 5 meters per second in the other direction, completely and directly opposite from me, or how I'm moving, right? So now we just need to do the same thing again, where we add two vectors together. So we have this minus v, this new vector that we've taken, and we want to add it with u. So not to make things too crowded, but we can move this up, just like we did with u here, and go along minus v instead of v, where we would, so if I, see these are the same, and these are the same. So instead of going along u and then along v and then we reach p, we go along u and we go along minus v. And that's how we reach the q vector. So that diagram is getting a little bit messy, but I hope you can kind of see how instead of going along u and then along v, how we get u plus v, we go along u and then go along minus v to get to q. Yeah. So the last thing, so we've seen that we can subtract two vectors, right? So what's the next operation that we can think of doing? The next thing we'll have learned as kids is multiplying two numbers together. So can we multiply two vectors together? And the answer to that is also yes. So there are two ways of doing it. But only really one is needed for the time being. So you can do what's called a dot product and a cross product. At least we can do this in three-dimensional space, so like the real world, which is what we'll really be focusing on throughout this lecture series. So the dot product is used really in kind of projections and kind of seeing how much of a crossover you can get between two vectors, right? So if let's define our dot product. If we have some vector v and some vector u, we can see the dot product, so v dot u, is equal to the magnitude of v times the magnitude of u times the cosine of the angle between them. Now, how this is kind of derived is not really too important, but using it can be. This is how we really define a dot product in 3D space. So let's think about what this is graphically, right? So if we have some x and y here, and let's say some vector v here, and some vector u here. This is the angle between them, so this is what we're taking the cosine of. Now the one thing about the dot product that is quite important is that it's also called the scalar product. So, or the scalar product. This means that when we take our two vectors, v and u in this case, and we multiply them together in this way, we're going to end up with a scalar. And that kind of makes sense, right? When we have the magnitude of v, so how big v is and how big u is, those are just normal numbers, right? Like our scalars from the beginning. Those are just going to be normal numbers that we can do anything with. And a cosine, again, is just going to be a normal number that we get spit out. So this is what's quite useful about the dot product, is that we have our cosine as well. So if you remember back from the beginning and using our trig functions and our trig ratios, we can use cosines and sines to kind of figure out different details. So let's go back to our graph, and let's see if we can shoehorn in a right angle triangle here. So if we were to like go down here, right, and make our say a right angle triangle here. In a way, this is what we call a projection. So we're taking v and we're kind of pushing it down onto u, right? And we're seeing how much of an overlap there is along u. And this distance here, we calculated at the beginning. So if we had this distance that's called d here. All right, so now that we have this distance d, which is you can think of as the vector v being projected or kind of pushed down. And the way that I was kind of taught was if you kind of imagine a torch shining light down on v, how much of that shadow is cast onto you, right? We can use our trig notation or our trig functions from the beginning to kind of find out this distance d. So if we were to take the distance here from the origin to this point at the top of v, this is the same as the magnitude. It's how big the vector is, right? It's the general size of it. So we said that the cosine of theta, this angle here, at the very beginning, we said this was be the same as d over the magnitude of v. D over this hypotenuse, the distance from the origin to v. So if we multiply both sides by the magnitude of v, we have v cosine theta is equal to d. Now, these two look kind of similar, right? So similar, in fact, that if we were to take our dot product instead, v dot u, and we were to divide both sides by u, which is a scalar, so as long as it's not 0, we can divide it, no problem. We get the magnitude of v times the cosine theta, which is, in fact, the same as d. So if we want to find how much v is being projected onto, or how much of v is being projected onto u, or this kind of distance d here, we take the dot product and divide it by the magnitude of u, which is something that will be brought over and is a pretty neat feature of the dot product. Okay, so now that we've seen one way of calculating the dot product, and this is big in understanding it from a geometric sense or graphical sense, there's another way of defining the dot product. And although it might look a little bit scary at first, or if we go high. This sigma notation, it might look a little bit scary at first, but it's nothing to worry about. And the way that we can do this is by breaking our vector up into its components. So in the same way, when we have a point P, and we break that up into the x-axis, the y-axis, and the z-axis, how much each of those are being affected, we can do the same with our vectors. So in this 2D way of putting it, we can define, say, the vector u here in terms of how much it's moving in the x-axis and how much it's moving in the y-axis. And the way that we do this is by defining other vectors that point in only the x-axis and only the y-axis to help us. So as we saw at the while we were learning about adding vectors, if we were to add vectors, graphically what that means is we are going along one a certain amount and then going along another one a certain amount. So if we were to go along, let's say, 1/2 of v and then u, so we would go 1/2 of v and then noting u's new direction and how much we're going along that, we go up 1 u and we'd end up around here or so. But that's quite difficult, right? It's not really intuitive to us, especially when we have two axes already being quite useful together. So instead of dealing with all of that and different vectors like so, we'll define two new vectors. We'll define them as, let's say, I, and I will point a little bit along the x-axis. It'll point exactly 1 unit along the x-axis. This is what we call a normal vector. And instead of having our normal vector notation, either the cap or the bottom or being in bold, we use a hat instead to notate that it's of unit length or normal. So this points only along the x-axis. It has no other components, only on the x-axis. And likewise, we'll define another j or j hat to point 1 unit along the y-axis and nothing else. We can generalize this to 3 dimensions and add in a k or a k vector, but for the time being, we'll just keep it with 2D. So instead of so now we have a new way of dealing with like u. So instead of just calling it u, we can say instead of let's say we're going for a walk. Instead of going 1u, so 1u vector, we can say go along, let's say 3 units along the x-axis, and then 2 units along the y-axis. Or we'll go I, and then another I, and then another I. And then j, another j. Right? So this is a new way of thinking about it. So instead of, we can think about it like we think of our coordinate spaces, where it's a certain amount in the x direction and then a certain amount in the y direction. But obviously, we're not going to say, call our u vector I plus I plus I plus, plus I plus j, because that's just confusing even writing it. But we can scale it. So instead of I plus I plus I, this is the same as saying 3i, right? It's the same as taking 1 and then just scaling it up to 3. Same here. Instead of going j plus j, or 2 j's, it's the same as taking 1j and just scaling it up to 2. So we can write u, the u vector here, as I plus I, or 3i plus 2j, right? And going 3i plus 2j will land us in the same place as just going up u once. So these are called the components of a vector. You can take components of however you like, but this is really how we'll be doing it for the most part, at least, because it's intuitive, simple, and as we said before, they are orthonormal vectors. So they're orthogonal, perpendicular to each other, and they're of normal unit length. So it makes life so much easier. And then if we were to do the same thing here with v, if we're going up 1, 2, 3 j's, and then going across 1i, we can say that v then is I, or 1i, plus 3j. Now this one, you don't really need to put it in, you don't have to put it in, but it makes the notation much more clear. So now we have u and v expressed in component form. We can now talk about how we define this dot product. So the dot product is defined as, we'll use n here. So this sigma notation you might not be too familiar with, but you'll get more and more familiar with it as the course goes on and as you go through physics and college in general. So we say that this is being summed over n, so for all the n that we deal with. Now really, in this case, we only have 2, so we can write that as the sum from n equals 1 to 2 of vn times un, right? And so what do we mean when we say v1 or v2? What we really mean is the first or the second component. Now, this can be a little bit tricky when you're dealing with i's and j's, because if I was to write v as 3j plus 1i, and then you're trying to add it or multiply it with u, and then you get like confused as to how, which ones match up with which. So the way that we get around that is by introducing another notational trick. So we can say, instead of using this I plus j format, we can say that it's the same as writing a 3 and a 2 and kind of closing around in brackets like this. And you can have vectors of any size, of any length like this. But it makes notating things a bit easier. So now that we've defined our u and v in component form and in our new vector format, we can see clearly that this 3 and this 1 are the first components, and this 2 and this 3 are the second components. So let's say when n equals 1, we have v1 times u1, and when n equals 2, which is our upper limit, we have v2 times u2. So our v1, we've made sure here is just 1, so we can write that as 1. Our u1, which we've discovered here, is 3, so we can write this as a 3. And then we add that together with v2. So the second one in the v vector, second component, is a 3. And the second component in the u vector is a 2. And then we just sum these up. We get 3 plus 6, which is 9. So now we've taken our scalar product, and instead of having to deal with cosine theta, which is finding the angle between two vectors, which can be annoying, we've discovered this new way of doing it, and we've gotten our 9 without having to worry about any geometric issues like that. You can go and find theta yourself and test it out, but it works out pretty well. Now this dot product works for 3D. It works for 2D and 3D quite well because we have this angle. We can visualize the angle between this here or the angle between, two things in 3 dimensions. But when we think about more abstract things, which will happen a lot more in maths, we don't really have the idea of a dot product. We don't really have this angle between two vectors thing. It doesn't really work because we can't visualize it. But this summation definition of the dot product does generalize. And it's in general called the inner product. But again, we won't have to deal with that for this course here. So we found our way to multiply two vectors. But there is another way, as I said, that works in 3 dimensions. And that's called the cross product. So really what that does is it takes, you can think of it as like a function, taking an input of 2 vectors and spitting out a vector that's perpendicular or orthogonal to both of them. But that's not really something we have to worry about too much here. This course won't really deal with the idea of cross products or too heavily. So if we come across it or if we need it, we'll explain it there. But it's something that you can go over and that isn't necessary for this course anyway. So we have discovered now that you can indeed multiply 2 vectors. So now the question is, can you divide vectors? This is the last of the arithmetic operations that we learn in school, and we can't really. There's no way to kind of think about dividing 2 vectors. There's no kind of graphical or geometric sense to it. And then in vector algebra, there's no kind of way we can think of dividing vectors, at least not in our sense here. So for division, we can't. So we have multiplication by a scalar. We've shown that we can do that. We've shown that we can add 2 vectors, subtract 2 vectors, multiply 2 vectors, and that we can't really divide 2 vectors. So that's really all we have to know about trig, coordinate spaces, and vectors for this course.